Welcome to Brain Vision.
We have a hydrogen atom in the n equals 2 excited state, and we're asked to find the radius of the electron in that state. So to do this, we're going to use the Bohr's radius, A naught, which is the radius of the electron in the ground state, which is 5.29 times 10 to the minus 11 meters, and the equation that says that the radius of the electron in a different excited state, N, is squared times the Bohr's radius. So plugging in our value for 2 and squaring that and multiplying it by the Bohr's radius, we find that this is equal to 0.212 times 10 to the minus 9 meters, or 0.212 nanometers. I'm going to write it as nanometers, but you could also write it as 10 to the minus 9 meters. For part B, it wants us to find the momentum of the electron at this distance. Of course, our equation for momentum, P, is equal to the mass of the electron, which is 9.1 times 10 to the minus 31 kilograms, times the speed of the electron, where the speed of the electron, V, is equal to the speed of light, C, divided by the fine structure constant, 137, times the orbit radius that we're at, or excuse me, the orbital that we're at, N. So plugging in that for our speed in our momentum equation, we find that P is equal to m times c, where again, m is the mass of the electron, c is the speed of light, divided by 137 times n. So plugging these values in, we find the momentum is equal to 9.95 times 10 to the minus 25, and the units are units of momentum, so this is kilograms times meters per second. We can box this in as our solution for part B. Part C wants us to find the angular momentum of the electron. So the angular momentum of the electron, we'll call L, is equal to, in this situation, we're using classical angular momentum. So this is mass times the radius of orbit times the velocity, V. So the mass is the mass that we found, the radius is the radius that we found in part A. You want to convert that to meters. So we want to use 0.212 times 10 to the minus 12 meters, since we're using SI units. And the speed, V, of course, is just the C divided by 137 times N. So this ends up being equal to M times R times C divided by 137 times N. Plugging these values in, we find that the angular momentum is equal to 2.11 times 10 to the minus 34 and the units of angular momentum in SI units are joules seconds. And that can be boxed in as our solution for part C. Part D wants us to find the kinetic energy of the electron. So the kinetic energy of the electron is defined, we'll call it Ke, is defined as the Coulomb constant, which is written as K sub little e. So this is the Coulomb constant times the charge of the electron, E, squared, divided by the 2 times the radius of orbit that we found in part A. Again, you want to use the units of meters there. And Ke is 8.99 times 10 to the 9. And of course, the charge of the electron is 1.6 times 10 to the minus 19 coulombs. Plugging these values in, we find that the kinetic energy for this electron is equal to 5.43 times 10 to the minus 34 joule seconds. It's much more convenient and intuitive to write this in units of electron volts, so we can convert joules, or sorry, not joule seconds, it's just joules. Yeah, because we're dealing with energy, and energy is written as units of joules. So it's more intuitive to deal with energy, especially when talking about electrons, in units of electron volts. So we convert joules to electron volts by dividing it by 1.6 times 10 to the minus 19. Oh, I'm sorry. I did make one more mistake. This is not to the minus 34. I'm sure you guys caught that if you were actually plugged in the correct values here. This is 5.43 times 10 to the minus 19. I was looking at part C where it's to the minus 34. So 5.43 times 10 to the minus 19 joules. We convert this to electron volts. This is equal to 3.4 electron volts. Apologize about that. But we box this in as our solution for part D. Part E wants us to find the potential energy. We're almost done here, just two more parts. So the potential energy from electric charge, we'll call this PE, is equal to, once again, you have the Coulomb constant, but it's negative, the Coulomb constant, K sub E, times the electric charge of an electron squared, divided by the radius of orbit, r. Again, use the value of meters for the radius of orbit. This gives us negative 1.087 times 10 to the minus 18 joules. Again, for comparison with what we did in part D, we want to convert this from joules to electron volts using the fact that 1 joule is equal to 1.6 times 10 to the minus or 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So this gives us negative 6.8 electron volts. And lastly, part F wants us to find the total energy of the electron. The total energy of the electron, which we'll call E, is just the sum of the kinetic energy with the potential energy. So this is equal to Ke plus Pe. Make sure you are watching out for your negative signs. So since Pe is negative, this is actually going to be 3.4 electron volts minus 6.8 electron volts. So our total energy value is going to be negative, and it's equal to negative 3.4 electron volts, which we can box in as our solution for part F. And that's the last part of the question.